In 1609, Johannes Kepler tried to explain the orbit of the planet Mars, publishing Astronomia Nova. He used the astronomical observations of his mentor Tycho Brahe, and he needed to find a better way to explain the orbit of Mars. There were three models of the solar system. The Ptolemaic system assumed the Earth at the center of the universe, with the Sun and the other planets traveling around it along perfect circles. Copernicus believed that the Sun was at the center of the universe, motionless, with Earth and the other planets orbiting it in circular paths. The Copernican system described the universe better than the Ptolemaic system. The Tychonic system combined aspects of Copernican and Ptolemaic systems. The Earth is at the center of the universe. The Sun, Moon and stars revolve around the Earth, and the other planets revolve around the Sun. All three systems used circular orbits and considered the speed of the planet as a constant. This is why the data didn't fit.
But these problems were solved by Johannes Kepler, an astronomer and mathematician who found that another shape, the ellipse, works a lot better. An ellipse looks like a flattened circle and it has some particular properties. We can draw one by taking a loose string, attaching both ends to the paper and using a pencil to keep the string tight while tracing the whole perimeter. The result is an ellipse. The sum of the distances between each endpoint or focus and any point on the ellipse is constant. After Kepler stated that Mars travels in an elliptical orbit around the Sun, he tried to extend this first law to include all the planets, and demonstrated that this shape was the better choice according to the available observations. The ellipse will be longer and skinnier if the two foci are farther away, and this skinniness parameter is called eccentricity. For example, comets can have very eccentric orbits. Instead, the orbits of the planets in our solar system are not very eccentric at all. They are very similar to a circumference, which is partly why perfectly round orbits seemed what to expect at first. It wasn't easy to abandon such a popular idea, but with the first law of planetary motion, Kepler first rejected circular orbits and showed that an ellipse could better explain the movement of Mars. Generalized to all planets, it states that the orbit of a planet follows an ellipse with the Sun at one focus. The position in which a planet is closer to the Sun is called perihelion. That in which is farther is called aphelion.
If you draw a line that is called the radius vector from the center of the Sun to the planet, the radius vector will sweep out an area that is the same during the time. So this is known as Kepler's equal area in equal time law. However, the planet doesn't move at a constant velocity, but it travels faster when it gets closer to the perihelion and moves slower when it gets closer to the aphelion. In the first case, the radius vector is shorter, but because the planet is moving faster, it covers a lot of distance. Whereas in the second case, the radius vector is much longer, but the planet moves slowly. The area that is swept out in the amount of time is the same. We can also explain the position of the Earth during the months. This works only with an ellipse, because with a circular orbit the velocity would be constant. The second law is a consequence of the conservation of angular momentum, that is the measure of the amount of rotational motion in a body or a system of bodies.
Kepler announced his third law 10 years later in his 1619 book Harmonices Mundi, or The Harmony of the World. Kepler's third law relates the distances of the planets from the Sun with the orbital travel times. By sifting through observations of how the planets move in their orbits, he noticed something new. The time it takes for a planet to orbit the Sun once, its orbital period p, is related to its average distance from the Sun, its semi-major axis a, in a very specific way. The square of the period is proportional to the semi-major axis cubed. In fact, if we choose our units carefully, with the period in years, the time it takes for Earth to go once around the Sun, and the semi-major axis in astronomical unit or AU, the distance between the Earth and the Sun, about 150 million kilometers, the proportionality becomes an exact equation. The square of the period is equal to the semi-major axis cubed. So, Kepler's third law states that the ratio between the cube of the semi-major axis of the orbit and the square of the period of revolution is the same for all the planets.